last time we talked about two different types of convergence. We have pointwise convergence versus uniform convergence. And one type of convergence is stronger than the other. The convergence we always talked about in Calc 2, just when we say convergence, that's pointwise convergence. Uniform convergence is a stronger type of convergence, and uniform convergence implies pointwise convergence, but not the other way around necessarily. So uniform convergence, you should think about the word uniform here. That's in the sense that here we have, first to frame the problem. I think that's very important to just first say, okay, what's going on? So remember here in this situation, we have a sequence of functions. So there's two kind of components to think about here when we're talking about a sequence of functions. One is we can evaluate the function at different x values. And the other thing is we have infinitely many functions to look at. For each number n, there's a function from this sequence of functions. So if you send n to infinity, for each n, that's a function. And then for each of those functions, you can evaluate it at different x values. Okay, so just, so here, the uniform convergence is implying that the convergence across all x values. So here, for this particular sequence of functions, for each n, the function looks like a diagonal line like this. So maybe this first one here is f of 1. That would be f sub 1. And then the second one down here would be f sub 2. There's a sequence of functions. And for each of these functions, we can evaluate them at different x values. So here's another f sub 3, for example. And so for each index n down here, for each index n, there's a function of x that's defined on the interval -2 to 2. So for each one of those, we can look, you can pick an x value and say for each one of those, what's the x value doing when we send, if we fix the x value and send n to infinity, what's happening? And so here we can prove that we have pointwise convergence, that if you pick each point and fix the point and send n to infinity, it goes to 0. But here we can show that the pointwise convergence happens in a very uniform way, in that here when this thing converges, so you should now kind of imagine the picture here. So here, imagine a bunch of functions here, and as n is going to infinity, these lines are getting more and more horizontal, and when n gets to infinity, right there, eventually it'll converge. Okay, so what you should notice about this picture is that it happens that all the x values, the function at all the x values, they all tend to move towards the limit. There's not one point or another that gets further away or gets left behind. There are no scragglers here. This sequence of functions very steadily converges in a nice picture. There's no scragglers, there's no points left behind. And mathematically, we can prove that with this statement. We claim here at any point in time of the sequence, for any n value, every point will be less than 1 over n, no matter where we are in the convergence. So let me say for a very large n value. So for a very large n value, maybe the function looks like this. So this is for a very large n. So even at this point, you can see uniformly, every function value is within this fixed distance here. That's a little low, try that again. Every point is within this distance. There's no point that's further out than that horizontal line I drew there, that second one. No, the way to think about convergence is that there's a target and we can specify a tolerance. So when I say tolerance, I can specify how close to the target we want to hit. The target is the limit of the sequence. And so if you say a sequence converges to its target, a way to think about it is for any tolerance that you specify, for any distance away from that target, I can tell you what n value we have to go out to in the sequence. So, if you want to be within 0.1 of the limit, go out to 10,000 terms, that kind of idea, just for example. So that's really a nice way to think about convergence as being itself sort of a function, an input-output relationship. I'll give it a tolerance of how accurate I want to be, and the convergence will spit out, the minimum number of terms to use. So here, the tolerance is always guaranteed, across all x values. We know for all x values, for any n, they'll always be within 1 over n of the target. So here the uniform convergence kind of standardizes the accuracy, the tolerance across all the possible x values, across all the possible inputs to the function. So here's a very kind of weird and tricky example. And this is, this is really nothing to do with Fourier series in the grand scheme of things. This is just an example of the concept of pointwise convergence versus uniform convergence. And we don't need to worry about the math so much. That you can look at it if you're interested in it and you like analysis. But here, let's just get the idea of what's happening. So first, I want you to think about this sequence of functions when n equals 1. It looks like this. It's starting out, its starting position is like this. That's when n equals 1. So this is when n equals 1. And now we're going to send n to infinity. And when n goes to infinity, what you should imagine is it kind of collapses, folds up like an elbow. Down here, it moves towards the left as n gets larger and larger. And in fact, we do a quick thought experiment here. Think about what happens to this interval as n goes to infinity. It collapses to 0. What happens to this interval as n goes to infinity? It collapses to 0. And in fact, as n goes to infinity, this entire part just basically disappears as n goes to infinity. And as n goes to infinity, the sequence of functions converges to the 0 function. That's when n is at infinity, quote unquote, whatever that means. But the way the function is designed, there's always going to be one point here at the crook of this elbow that's going to be a fixed distance of 1 unit away. So there's always going to be, no matter what n value you pick, there's always going to be one point where the distance from the target is a fixed distance of 1 unit away. And so here, the convergence isn't uniform. There's always one scraggler. There's always one point that's like, hey, wait up, guys. There's always one scraggler. There's always one point left in the back that's like, I'm coming, and it's always a fixed distance 1 unit away. Now, this is the tricky part. This is the part that's counterintuitive. When n goes to infinity, then these intervals collapse to 0 here, and the only function we have is the 0 function. So this does converge to 0. It converges pointwise, but for any finite number n, if you pick it, you'll get one of these weird spike functions. And the convergence is not uniform because, you can see from the picture, there's always going to be a point that's a fixed distance 1 away from the target. There's always going to be one point that's a fixed distance one away. And so we can't do this kind of the technical definition of the uniform convergence. We should be able to say that the limit of the maximum of the vertical separation between any sequence in our sequence of functions and the target where it's converging, that maximum vertical distance goes to 0. Here, the maximum vertical distance is always fixed at 1. There's always one point that's, a fixed distance 1. So here we don't have uniform convergence. So yeah, it's a little weird, and it's definitely a deep concept, and we don't figure it out in 5 or 10 minutes, right? And people who've been working on this theory, they spend their whole lives working on this theory. And so, yeah, this is a nice counterexample from analysis. I won't worry about the technical details too much. You can get the idea of what the picture's doing, and the idea that for any fixed n, we're always there's one point that's a fixed distance 1 away. But as n goes to infinity, this is the part that's counterintuitive to the brain, and this is the reason we do math, to understand these things. When n goes to infinity, however, the region, the region where it's not 0, the support of the function collapses to a set of measures 0. There's no domain for where it's not 0, and the entire thing is just 0. Okay, so let me talk about one last type of convergence. And this is the strongest convergence we could have. So in order of convergences, pointwise convergence, is your basic type of convergence. Uniform convergence is really nice. That gives you uniform accuracy across your level, your choices of X values. And then there's absolute convergence, which is the strongest type of convergence for this analysis. So let me just say, traditionally, if you read the literature, uniform convergence and pointwise convergence is typically only discussed in the context of sequences specifically, and absolute convergence is typically only discussed in the context of series, even though a series is a sequence. So those three convergences are really, at the end of the day, all referring to sequences, keeping in mind that a series is a special type of sequence. So the Fourier series is said to be absolutely convergent if essentially we can show that the tail is going to 0 very fast. And this isn't a great definition. So here, you should be careful. Think about what you're looking at. So here, this is what we call the tail of the series. These are, infinitely many points starting from some fixed number. So starting from 10,000, these are the points 10,000 to infinity. This is what we call the tail of the series. And if the tail of this series goes to 0 fast enough, then we have a very strong convergence. And so this definition here is saying that we have a very strong convergence. I prefer this definition, is a little better here. So here, if we can show that it's basically very similar to absolute convergence for a regular series. So absolute convergence for a regular series, remember, is if this happens, if you have just a regular series of numbers, not functions, not Fourier series, sigma a sub n, if you now take the absolute value of the terms, and now if you can show this converges, so this is a finite number. So when you take the absolute value, think it through now. If the series diverges, the only way it can diverge is by blowing up to infinity, since we've taken the absolute value. Every term is either 0 or positive now. And so you add infinitely many terms that are non-negative. If it is to diverge, the only way it can diverge is to infinity. So here, if I can show this is finite, and here, obviously, this is greater than or equal to 0. If I can show it's finite, then remember we said the original series is absolutely convergent, blah, blah, blah. So it's the same idea here. We're just taking, well, I said that like I was from New York. It's the same idea here. We're taking the absolute values of the terms of the sum and doing a triangle inequality. If we can show that converges, then that's absolutely convergent. So now we'll get some nice theorems that tell us when we have absolute convergence. So, don't worry about it too much. We'll connect this all back to some stuff we did in Calc 2. So, okay, here's the hierarchy of convergence. Absolute convergence implies uniform convergence. Uniform convergence implies pointwise convergence. Okay, but going the other way is not true. Pointwise convergence does not imply uniform convergence. We have an example of that. And uniform convergence does not imply automatically absolute convergence. So here's a test for when a series of functions is absolutely convergent. It's called the Weierstrass M test. So here, if we have a sequence of functions defined on some set, and M sub n here, this is a sequence of non-negative numbers, just like a regular sequence from Calc 2. This would just be like a regular sequence from Calc 2, just a sequence of numbers. And if the sequence of functions, the absolute value of each function is bounded by that sequence of numbers M sub n for all x, you know, where the function's defined, then we can conclude that so get the conclusion here, the series of functions will converge uniformly if the series of constants that it's bounded by. So here, this is just like a regular series from Calc 2, where it's just a series of constants. There are no x variables in there. Here, this is a series of functions where there's an x variable in there. That's like a Taylor series or a Max series or a Fourier series in this context, right? A Fourier series. And so if the regular series of constants here is absolutely convergent, in the usual sense, we take the, we don't have to take the absolute values because M sub n are already non-negative. So if this thing just converges, like if it's a geoseries, or if you use a ratio test or a root test and just show that it converges, direct comparison test, whatever, then if that thing converges, then the series of functions here, series of the, sum of the functions will converge uniformly. So that kind of makes things, easy to do in terms of the analysis. It allows us to connect back up to Calc 2 series when we can. And we'll come back to that a little bit later, that result. So let me talk about Gibbs phenomenon now, because the uniform convergence has everything to do with Gibbs phenomenon. So Gibbs phenomenon is this persistent overestimation or underestimation. It's called an overshoot or undershoot at jump discontinuities of the Fourier series. Of the truncated Fourier series, I should say. So the truncated part is important. If we use all infinitely many terms, in theory, all infinitely many terms converges to the original discontinuous function. That's the part that's counterintuitive, that the space of trigonometric polynomials is dense in the continuous functions. It's just like E is a limit of rational numbers, but is itself not rational. Yet somehow this sequence of rational numbers converges to a number that's irrational. That's what happens here. Technically, if you use all the terms of the Fourier series, it's converging to the original, perhaps discontinuous function. So for the truncated Fourier series, we get Gibbs phenomenon. And this has everything to do with the type of convergence, and here it doesn't go away. That's the thing with the Gibbs phenomenon. It doesn't go away. Usually in certain numerical schemes, if you use more terms, it gets more accurate. Here, the more terms we use, it's a persistent issue. It doesn't go away. And in fact, it has a limiting value. In fact, it'll approach the discontinuity closer and closer, and there's a limiting value to the size of the hump. I'll show you here, to the size of the overshoot or undershoot. So I did a numerical experiment with this discontinuous function here. It has a single jump discontinuity at the middle and at the endpoints. So here's the Fourier series. I'll let you check that. And so what I'm going to do now is plot various values of the truncated Fourier series. So here's the original function with this jump discontinuity at the origin, and its endpoints aren't equal. So we expect the truncated Fourier series to do smoothing, right, and averaging. So here I graphed, this is using the first 5 terms. And so you can see the Gibbs phenomenon right here. And in particular, the way I want you to analyze this in your mind is to say, well, the accuracy here and here is less, way less than the accuracy here and here, you know. And this is a visual example of point-wise convergence versus uniform convergence. So these points are converging, but very slowly, a lot slower than these points. These other points are converging very fast, you know, comparatively. And so the convergence here for all x values is not uniform. Yeah, they're converging, but there are some stragglers. They're not all approaching, you know, within a same tolerance. So here's 10 terms. So you can see the Gibbs phenomenon, it's not getting better. Here's 15 terms. Here's 20 terms. So you see the Gibbs phenomenon doesn't get better, but it does seem to have a fixed height. And here you can see the pronounced difference between, you know, this is a great picture of pointwise convergence where you have better accuracy at some points and worse accuracy at other x values. So you can analyze the Gibbs phenomenon, you know, you can just use regular calculus. You can see the Gibbs phenomenon will be where we have a critical point where the derivative of the Fourier series will be 0, and it'll be the critical point that's the closest to the discontinuity. So just by taking the derivative, remember here, this is not an infinite series. This is a Fourier series with, you know, truncated after 20 terms. So this is just like a regular function. Take its derivative, find out where the derivative is 0. The zeros closest to the origin will be the Gibbs phenomenon jumps here. And then we can measure, then we can actually measure what this height is, you know. So it's not difficult math, it is tedious math, you know, so I'm not going to do it, but that's how one can analyze Gibbs phenomenon if one wishes to. And I'll give you a reference at the end. So what's the deal here with Gibbs phenomenon? You know, so in analysis, the result that's proven is that a sequence of continuous functions, for example, like the partial sums of a Fourier series, cannot converge uniformly to a discontinuous function. You know, and here's where we sort of reach the limit of the theory. This makes sense, you know, we can't ask a continuous function to converge uniformly here to a discontinuous function. And so that's why we have pointwise convergence, which is very nice, but we don't get the uniform convergence. So if our adjusted periodic extension of the function f that we're finding the Fourier series has a jump discontinuity, then we will have pointwise convergence from Dirichlet's theorem, but we'll get different tolerances, different rates of convergence. The convergence will not be uniform, you know, it's not uniformly convergent, and therefore it will also not be absolutely convergent, since absolute convergence implies uniform convergence. And at the discontinuity, we will see Gibbs phenomenon. So yeah, so, and if you have a Fourier series that does converge uniformly or absolutely, then it will not have Gibbs phenomenon. And I'll talk about a theorem for when that happens. And in general, if f tilde is continuous and, you know, f tilde prime is piecewise continuous, then we typically, I think, can expect absolute convergence. I think there's always these one-off weird counterexamples, but just as a general comment, continuity of f tilde goes a long way. So just a couple of things to clean up couple of concepts here very quickly. So with uniform convergence, we can conclude that if the sequence, if each function is continuous, then the function that the series of functions converges to will also be continuous. So sum of continuous functions, infinitely many continuous functions will be continuous if we have this uniform convergence. And we can bring the integral inside the sum, okay? And we can bring the derivative inside the sum if the series of the derivatives of the, you know, of the functions converges uniformly. So let's just let you look at these. These are just when can we integrate term by term and differentiate term by term. Generally, we'll assume that we can do this and just do it without worrying too much about it. So for uniform convergence, we do have a theorem. If the function we're starting with is continuous piecewise smooth, so that means the function's continuous and its derivative is piecewise continuous. And it's adjusted at the endpoints, either we can, and it's equal at the endpoints, then we can show that convergence is in fact uniform. So that's a, we won't prove this, but this would be a stronger uniform convergence theorem for Fourier series that we won't prove. But yeah, so if you have fx being continuous piecewise smooth, then we get a really nice convergence. And that's not too much to ask. The continuous piecewise smooth is not too much to ask. So here are some general references. The Pinsky reference. So this is the PDE's book we used to use a long time ago. And then at some point it was decided to switch over to Haberman. So, there's no such thing as a perfect textbook, and they're both good in their own way. Pinsky is a little more analytic. It's a little more technical, and there's more analysis in Pinsky. So if you're interested in those details, and Pinsky does the analysis of the Gibbs phenomenon as well. So there is a copy of Pinsky's book at the library, the math library. And then Bleecker and Sordas is just a general partial differential equations reference, which I've mentioned before. It's just in general a good reference that covers the history, the analysis, as well as the PDEs. So that ends the analysis portion. And so now I'm going to switch over to the slides and talk about the derivation of the heat equation. So we've concluded the analysis regarding the convergence behavior of a Fourier series. In that portion of the class, we're just treating the Fourier series as a mathematical object and analyzing its behavior. What is it? How does it act? When does it converge? What type of convergence? Now we want to start to use the Fourier series as part of a plan to solve PDEs. Okay, so the first fundamental equation we're going to look at is the derivation of the heat equation. There's some preliminary remarks that I've put here that I'm not going to go into too much. So one thing we will do frequently is bring the derivative inside the integral. So this preliminary slide here, preliminary remarks, addresses when that's possible. And there are actually, these are actually a little more strict than necessary. I believe there are even looser conditions than this that are necessary. But anyway, I'm not going to get into it, but I'll let you look at this if you're interested. But under certain conditions, it's okay to bring the derivative inside the integral. In general, in analysis, this is kind of a complicated question, and it has everything to do with uniform convergence. Okay, so I'm just going to leave it there and move forward. So we want in the heat equation, so PDEs is traditionally called applied math because the problems that motivate the equations in PDEs are physical problems. But it's not that we actually do anything physical. It's just that conceptually it's motivated by a problem in reality, supposedly, in our fake reality in our mind. So here, we're trying to model the transfer of thermal energy, temperature change. We, for now in a one-dimensional rod. And so here's the rod, and you have one end at x equal to 0 and one end at x equal to L. The lateral sides here are insulated. So heat cannot, enter or go out of the rod through the lateral sides here. The only place heat might go in or out of the rods is through the ends, okay? If the ends are not insulated and there's a heat, so blah, blah, blah. But if we insulate the ends, then that would not be the case also. So, but that's the game we're playing, okay? So what we want to now do is come up with a mathematical formula for this concept we're calling the thermal energy density. The thermal energy, I'll let you, what the word thermal and what the word energy means. So I'll let you in your mind conceptualize, okay, thermal energy. And so here we want to find a math equation to describe, the thermal energy. So we introduce this concept called the thermal energy density, which describes the amount of thermal energy per unit volume. Okay. And so now we're going to slice up the rod and take a little thin delta X slice, and here, let's pull that out. Take a little thin delta X slice of the rod, and where we know the area of the face here is some positive constant A, that's the area. And so if I multiply area by the thickness, I'll get the volume. And so if I want to calculate the heat energy here, the total heat energy in this little slice, I can do the energy per volume, the energy density of that slice, which I'm going to approximate with a constant because the slice is so super thin, even though, it looks thick on my slide, it's super thin. I'm going to estimate the energy density of the constant, multiply by the volume. That'll give me the heat energy in that one little slice. And then we play the calculus game. The calculus game is, now integrate from 0 to L. And so now I know I have an expression for the total heat energy. Okay, so the heat equation derivation involves 3 equations. And so right now I'm motivating the main equation on top, and then there are 2 more equations, and then we put them all together and you get the heat equation. Okay, so the next concept, so the heat energy that I just described on the previous slide, that's the left-hand side of the equation. Okay, I'm going to now talk about the heat flux. The heat flux is what will show up on the right-hand side of the equation of our heat equation. Okay, so just go slow. It'll seem random, but it'll all come together at the end. I'm trying to define, an equation. So left-hand side, the right-hand side, and then we'll equate the 2. Okay, so the heat flux. Yes, go ahead, please.
So are we assuming the rod is generating heat or just transmitting it?
We will assume that there's an internal source of energy down here as part of our model. So there's the rod. There might be some internal source of energy within the rod, and it might be subject to energy fluctuations at the ends.
Right. Okay. Yeah. So we'll have boundary conditions, and then we'll also have internal generation.
Yeah, but we'll probably just make the internal generation 0 because this is a pure math class.
Cool.
But yeah. So the heat flux, again, you should have to use your imagination to think about what heat flux is. It's the amount of thermal energy flowing to the right per unit time per unit surface area. Okay, so if capital phi is negative, then the energy is flowing to the left. Remember, this is a one-dimensional rod. And so now I'm going to come up with a mathematical expression for the heat energy flowing across the boundaries of this little slice x plus delta x. So here, here's your heat flux flowing to the right. So at the left here at x, it'll be flowing in if phi is positive. So let's just assume phi is positive for now. And at the right here, the heat flux will be flowing out. Okay, so I'm going to calculate the amount of heat energy gained is phi of xt times A. So here, remember, this is per unit surface area, and I'm multiplying by surface area. So now I'm just getting the amount of total energy flowing to the right per unit time. That's what I'm getting now. And that's at the right. At the left, it's losing heat. So here, I have a minus sign here to indicate heat loss here. So here, heat energy lost at x plus delta x, assuming phi is positive. Okay, so now to make this more calculus friendly, okay, so now some math trickery. I'm gonna factor out this minus sign all the way out and write the phi of x plus delta x term first. So here, this is just to make it more calculus friendly. Here, if you distribute the minus sign, you get exactly back to this term, and this is the energy flowing in on the left side. This is the heat energy flowing out at the right side. And this is a little more calculus friendly, and we will write this in a more calculus way in a second. Okay, we'll write this as, you can think of this as f of b minus f of a. And so we will write this as integral of the derivative of the heat flux from x to x plus delta x. We're going to get an integral equation, at the end of all these manipulations. Finally, in the model, we allow for an internal source of energy. So Q of xt will be the heat energy generated per unit volume per unit time within the rod. And so this could be due to a chemical reaction or electrical heating, or you know better than I do, radiation, I don't know. So here, just multiplying Q of xt, which is, per unit volume, by the volume, gives us the heat energy per unit time generated inside the rod. And, starting out, we do baby steps. So starting out, we'll assume Q is 0. Starting out, we'll start some easy situations, and then we'll make it more and more complicated. We will look at situations where we have internal sources. So, all right, here it is. Here's the conceptual basis for the heat equation. And so the sun's coming through my skylight here, so my apologies. So here we go. Here's a word equation. So we have the rate of change of heat energy with respect to time is equal to, so this is the fundamental heat process in the rod. Okay, so think about the rod here. The rate of change of heat energy with respect to time of the rod is basically going to either be due to heat energy flowing across the boundaries per unit time, or, so we add, or due to heat energy generated inside the rod per unit time. So we calculated the heat energy was the integral of e to the xt. So this expression on the very first slide, this was the heat energy. So I'm taking the derivative. So this is the rate of change with respect to time. I'm taking a derivative of the heat energy right here. And on the other side, the energy flowing in through the ends would be phi of b minus phi of a, right? Before we had, instead of b here, we had x plus delta x, and here we had x. So now we'd go all the way to a and all the way to b. You can basically sum each of the delta x slices and get this expression. Times a, for the heat energy, plus the heat energy generated inside the rod, if any. So yeah, and so now we can cancel the a's. So here now we're going from the physical model to now to a mathematical model. It's going to be maybe make less sense physically because we're now going to cancel the a's. Those are just a constant. We get this equation. Now we're going to, and then here's where I rewrote this. So careful. I rewrote this as the integral of the partial of phi with respect to x. So this is just fundamental theorem of calculus, right? The integral of the derivative is the antiderivative. So here, this is just writing f of b minus f of a as integral of capital F prime from a to b. And now we bring everything over and make it one giant integral and set it equal to 0. And this is called the integral conservation law. And now this is some subtle analysis, but it can be shown that this integral holds for any choice of values a and b within the rod. So what that means is the integral is equal to 0, not, it's independent of your choice. Doesn't matter which points you pick on the rod, is that the integral is always 0. So the integral is 0 independent of where you are on the rod. And so mathematically, since the integrand is continuous, the only way that can happen is if the thing we're integrating is 0. So from here to here, the big leap, the analysis that's involved that we're not going to do, is that if the integral is 0 for all values a and b, then the thing we're integrating must be equal to 0. So that's the thing. So the integral conservation law, that's the integral of this expression equals 0. And then we conclude, because it's true for all values a and b, the only way it can be true for all values a and b is if the thing we're integrating is itself identically equal to 0. And so finally, you isolate the derivative of the thermal energy here, the heat energy on one side here. And so this is the first equation. So this will eventually become the heat equation. So the next two things we'll do, and I think I'll be able to get to one of them. The next two things we'll do is write E in terms of temperature. So we want to introduce temperature as a new variable. And then we'll write this other expression here, phi, in terms of temperature. And then we'll have what we call the heat equation. Okay. And what I want you to notice, this is a PDE. What does that mean? There's a T derivative here. And quite separately, there's an X derivative here. One's a time derivative, a temporal derivative, and one's a spatial derivative, a derivative with respect to space. And so these are kind of two very different types of variables, right? So okay, this is the top level equation. You know, I think it's good to see the big picture. So now what we're going to do is I'll write E, the heat energy, in terms of temperature. And then we'll write phi in terms of temperature. And then we'll put all those things together and get the heat equation. So let me now write the heat energy in terms of temperature. So by the way, before I go any further, let's just think about this intuitively and motivate the minus sign. Okay. So here, I think, you know, it helps to not just reduce this to a bunch of equations, but let's think about this minus sign and why that would be there. Because, you know, one question is, why the minus sign? If this is math, can't we just absorb the minus sign into the function and just write it? You know, so this is conceptual. So do a thought experiment with me. Assume the spatial derivative of phi is greater than 0. So what does that mean? As you go from the rod physically in space, as you go from the rod from left to right, the heat flux is increasing. Here, phi is an increasing function in x. So as you go from left to right, the heat flux gets larger and larger. So what does that mean? The heat flowing to the right at x equal to b. So, you know, if we're looking at our rod, let me put a little rod in here. If we're looking at the rod, what we're saying, if phi is positive, if the derivative here is positive, if phi is an increasing function, then phi at the right here of the rod will be greater, the phi value, than at the left. So that means there's more heat energy going out at the left than there's heat energy coming in. So, you know, if you assume Q is 0, for example, then we would expect the overall heat energy to be decreasing. And so here, if the derivative is positive, the heat energy will be decreasing according to this equation, and it fits what's happening physically, because phi at B is greater than phi at A. So the rod is losing heat energy. So expect the rate of change of the heat energy to be negative, which it is here, if you know. So, and we'll do that again with some other equations. And, you know, start with assuming Q is 0 and think about what it means if you have more heat energy leaving from the right end than the left end. Okay, so here, if we define U to be the temperature, so now we're introducing temperature, okay, as this other concept. Temperature of the rod at point X and at time T, and keep in mind, so temperature or thermal energy would be synonymous, okay? This idea of temperature or thermal energy. And so keep in mind here that the amount of thermal energy required to raise the temperature of a material depends on the material. You know, some metals will heat quicker than others, right? And so we introduced the concept of heat capacity, or also known as specific heat. So this is the heat energy required to raise the temperature of whatever substance, to raise it 1 unit. So the heat capacity for steel would be different than the heat capacity for copper, right? I guess. I have no idea. I've never burnt either one. I'm a mathematician. What do I know? You should tell me. So here, in theory, the heat capacity should be a function of your location along the rod and the actual temperature. And that makes sense. As you heat something, its physical properties change, but that's too complicated for right now. So typically we will assume the heat capacity is just a function of X or is just flat out a constant. That's actually more frequently what we'll do, is just assume that the heat capacity is a constant. And so now an alternate description of the thermal energy, which is E. So here, E here, we'll find a description here that'll connect it up to heat energy. The amount of energy, so I don't know if they should say heat energy here, is the amount of energy needed to raise the temperature, needed to raise the rod's temperature from 0 to the actual temperature U of xt. So now I'm going to come up with a different formula for the heat energy. Okay, so let's assume we know the mass density of the rod, right? A very common thing that we do in these applied situations. So that's something we know from, measurements. We know the mass density of the rod. So let rho be the mass density of the rod. Then I claim the heat energy, another expression for the heat energy, which is E of xt times A delta xt, so here I think of this as the heat energy per unit mass. So the way I interpret is C of X describes the amount of energy, C of X tailors it to that material. C of X takes into account the material properties, and U of xt is the temperature. So the material properties combined with the temperature is describing here the heat energy per unit mass. And then we multiply that by the mass. Here, this is just density times volume. And so we come up with an expression for heat energy, but we already had an expression for heat energy using this energy density. And so from the first slide, we had this energy density times the volume is the heat energy, but here we have the specific heat times the temperature times the mass is also the heat energy. So we are able to equate these two and come up with our second equation. And here, the idea now is to relate E to temperature. And that's what this equation does. And I'm going to stop right here. And the other thing to do is to equate phi to temperature. And then once we do that, we'll have a single PDE in the U variable that we'll call the heat equation. So think about the physics of this, and I'll think about it too as well. And we'll pick it up here and finish the derivation of the heat equation next time. So I'm going to stop right here. Thank you for your time, everybody.